Yes, thank you very much for having me. So wait, I'm just sharing the screen. Okay, so thanks for having me. Hi, everyone. So my name is Anthony Chrun. I'm a master student at Polytechnique Montreal, and so one of the developers of the Chapel MultiPhysics Simulation Software, CHAMPS. And so for today's presentation, the goal is to share with you all the recent developments that we've been developing over the past year with the team, and especially the advancements of Baptiste Arnoux, Karim Zaini, Guillaume Auger, Maxime Blanchet, and myself, who are all supervised by Eric Laurando, who you may know very well by now, and also the work of Justin Rigal, who is supervised by Professor Roberto Paoli, who is a new professor at Polytechnique, who has recently joined and has adopted the CHAMPS software for his research as well. So let's dive into it. So for today's presentation, I'm going to focus more about all the physics that we can capture with our software. And so I'll give a quick context about the role of CFD and the integration of CHAMPS as a CFD software. And then I'll dive into the advancements, first starting with the multi-fidelity flow solvers, and then about the multiphysics solvers. And then I'll give a quick word on the CHAMPS high-performance computing benchmarks. So to give a bit of context, the airplane industry has set a common goal for manufacturers to reach net zero carbon emissions by the year 2050. And so there are multiple key areas of development in order to achieve that target. For instance, the development of sustainable aviation fuels, operational improvements such as optimizations in air traffic and flight planning, and crucially, new aircraft and propulsion technologies such as more efficient engines and better aerodynamics. And so talking about aerodynamics, this is one of the key aspects in emissions reduction, as the one very important feature of aerodynamics is the lift to drag ratio. And so this metric basically dictates the range that an airplane can achieve. And so we can see here down below in what's called the Breguet equation, is that for a target fixed range of an aircraft, increasing the lift to drag ratio will induce a reduction in fuel consumption. So this aligns perfectly with the goal of reducing emissions. And so in order to perform aerodynamic analysis, we have three main tools to achieve that. And so they are computational fluid dynamics, CFD, wind tunnel testing, and flight testing. And so obviously, wind tunnel testing and even more so flight testing are very costly and long to run. And so typically, these are reserved for later stages of aircraft development. And that means that CFD is actually nowadays is the main tool for aircraft development and design. And so wind tunnel testing and flight testing have become only validation steps for CFD. So CFD has become a crucial tool and a necessity for aircraft designers. And so the study of the aerodynamic flow alone is not quite enough, as in flight conditions, there are also multi-physics phenomena, such as the accretion of ice on the wings of an aircraft, and also the bending of wings during flight. And so those two phenomena can impact quite significantly the performance and the safety of the aircraft. And also there is a phenomenon which is the formation of contrails that is estimated to have quite a big impact also on emissions. So in CFD, there are quite a vast arsenal of tools that we can use, ranging from low fidelity models, from the vortex lattice method and potential flow method, all the way to higher fidelity methods like the LES or large D simulation, and even the direct numerical simulation. And so those tools all have their use case, as the low fidelity models are quick to run, and so quite efficient. And so they're typically reserved for initial development, whereas the higher fidelity models provide more accurate results for later stages of development. And so we've got in the ChapelCon software almost all of those models implemented and ready to use. So the solving strategy in CFD is the following. So most CFD solvers use the finite volume method, which basically means that we discretize the fluid domain into a mesh that's composed of multiple thousands or even multiple millions of cells. And so the meshes are 2D or 3D, and they can range from a few million to 1 billion unknowns. And so the sheer scale of the system we are trying to resolve here means that CFD has to leverage high performance computing in order to significantly reduce the computation time in order to achieve acceptable wait times. And so in order to do that, how it works is that we subdivide the problem into smaller subproblems that are interconnected via each other using interfaces. And then each subproblem is run independently on a dedicated task or a dedicated CPU in that case. And so the Chapel MultiPhysics software, or CHAMPS, is one of those software. So it's a pretty advanced one, as it's a 3D unstructured Navier-Stokes solver. We have a few schemes for the convective fluxes implemented, as well as multiple turbulence models ready to use. And so, as I've said before, we've got a range of multi-fidelity solvers, ranging from low fidelity to high fidelity solvers. And we've also, over the years, implemented multi-physics solvers in order to capture all the different phenomena that we can encounter in reality, such as icing, switch factor interaction, and control formation. And so with all of those solvers implemented over the years, the CHAMP software actually reached about 150,000 lines of code, which makes it one of the biggest Chapel code in existence. And so, yeah, I'm going to dive into the novelties of the CHAMP software. And so I start with medium fidelity solver, which is the full potential solver that leverages the MS boundary method. So to give a bit of context, in CFD traditionally, we use body-fitted meshes, which means that our cells basically wrap around the structure. So yeah, they wrap around the structure, which means that in order to mesh quite complex geometries, the user can encounter a bit of difficulty to reach an acceptable mesh quality, and it would take a lot of time to make those meshes. And so one solution to that is the MS boundary method. And basically this method allows us to use a fully Cartesian mesh, which is basically a mesh that's composed of perfectly squared elements. And so this significantly reduces the meshing time, and it simplifies the handling of the geometry. And those benefits are really important and really useful when doing preliminary design phases. And so this is why we're using it with the full potential solver. And so the applicability of the immerse boundary method goes even further, because it can also help multi-physics solvers that involve moving boundaries, such as icing and error elasticity. So here are some results of the full potential immerse boundary method. So here we're comparing it to a traditional body-fitted method, and we're also comparing it to a solver that's a slightly higher fidelity, which is the Euler implicit solver. And so what you're saying here is the pressure coefficient distribution on the NACA12 airfoil, so the traditional airfoil. And so we can see that the main differences here are the shock position when the Mach number reaches transonic speed. We can see that the shock position and the shock strength is different for the flow potential, and that's due to the isentropic assumption of the model. And then if we compare the body-fitted method against the IBM method, we can see that the IBM method yields oscillations near the trailing edge and a reduced smoothness. And this is most likely due to a mesh size that is a bit too coarse for the IBM method. Next up, we have the high fidelity models. So the first result here is for our Reynolds-Averaged Navier Stokes or RANS solver. And so in this one, on the left, we can see the pressure distribution on the wingspan of the common research model in transonic regime. And so we can see the shock position that's highlighted with on the wingspan. And on the right, we can also see the skin friction coefficients of the same aircraft in high lift conditions. Next up, we have a slightly higher fidelity model, which is a hybrid between the RANS and the large eddy simulation model. And so in this one, basically, we use the RANS model near the boundary layer, and then the higher fidelity large eddy simulation model in the rest of the domain. And so we can see that the LES model is capable of capturing smaller vortices and smaller structures of the flows. And finally, we have the DNS, or the direct numerical simulation. And so what you see here is initially a flow, large flow structure that are organized. And then over time, we can see that these structures stretch and distort. And so there is a gradual breakdown from large scale structures to smaller turbulent eddies. And so basically this shows that the DNS here is able to predict that breakdown from an organized flow to a homogeneous isotropic state. And so all of these simulations show that LES and DNS are models that are capable of capturing the onset, the growth, and the saturation of turbulence, which is not something that the lower fidelity models are able to do. Next up, we have the MultiPhysics solvers, and I start with the fluid structure interaction solver that now has the ability to handle nonlinear large displacements. So basically how this works is that we are coupling a flow solver. So in this case, it's a RANS solver, medium fidelity, with a finite element method structural solver. And so it works sequentially at first. So we have a flow solver that computes the external loads on the structure. And then those are fed in the structural solvers that yield displacements. And then those displacements are fed back into the mesh of the flow. And so this process is iterative, which means that for each time step, we are looping multiple times until we reach an acceptable convergence. And so this makes it strongly coupled. And so here is one result of that solver. So this is the box cantilever FSI validation case, where basically we have a rigid box that generates vortex-induced vibrations on the beam tip. And you can see that over time, the oscillations increase until they reach a steady oscillatory state. Next up, we have the aeroicing solvers. So this is one new feature, which is the Lagrangian particle tracker. So how this works basically for the prediction of isoaccretion is that we have ray tracing algorithms for efficient droplet quad intersection detection. And so we have a hybrid polarization that is done in Chapel in order to accelerate the computation of trajectories of the particles. And so this allows for a scalable framework that's capable of tracking tens of millions of particles at a time. And so this allows us to yield the water collection efficiency, which is then used as input to the isoaccretion simulation. And so here are the results. And we can see on the plot here that the chance prediction with the icing software using the Lagrangian particle tracker yields pretty good result, and it agrees pretty well with the experiments, as the shape of the ice structure is really the same. And also a word on the scalability. So for this particular solver, a scalability test was run on the Niagara cluster, which is a Compute Canada cluster. And so here we are comparing the total computation time. And so we can see that up to 32 nodes, the solver still reaches an efficiency of 86%. And so this result is quite satisfying. This is pretty excellent for a lab software. And so there is a second feature for the icing department, this time using a different approach. So this is not, unlike the previous one, a deterministic approach to icing, but a stochastic approach to icing. And it uses the IMUS boundary method that I've talked to you about previously. And so this is one of the application of the IBM method. So the stochastic approach means that the water droplets are seeded randomly, and then the solver computes whether or not the droplets freeze when they reach the wing. And so this is done iteratively until we reach a significant ice shape. And so we can see that with that approach, using the IBM method, we can see that the shape of the ice, so in this case, they are ice feathers, are pretty well reproduced by the stochastic model. And we can also increase the number of layers in order to increase the resolution of the simulation. And so this highlights the importance of a finer mesh to capture smaller scale structures of ice. And so finally, the last new feature I will showcase to you today is the formation of contrails. So what you're seeing here is a simulation of downstream of a jet engine. It's an actual Safran engine using a RAN solver. And so that engine is operating at flight conditions. And so here you can see the plots of the velocity, the pressure, and the temperature downstream. And so here is a comparison of the mean stream traces of the flow that are computed by the RAN solver, and another approach, which is stochastic, that is basically based on the Langevin model. And so this stochastic approach shows that qualitatively we get the expected dispersion and turbulent vortices. And also for the particle distribution, we can see with the stochastic model that we get a more realistic dispersion of the ice crystal particles compared to the mean approach. And we can also see that the radius of the particle is way more uniform than the mean approach. And so overall, here are the results of the solver. So this simulation was done on a 5-second simulation with 25,000 particles. And we can see basically where the particles activate. So basically the activation point is the point where the soot that's produced by the engines turns into ice crystals. And then those ice crystals grow steadily in time with the distance. And they will reach a steady value. So here it's about 500 nanometers. And so the formation of ice crystals is what causes radiative forcing, which is the root cause of emissions due to contrails. Okay, so now a word about the chance polarization performance using HPC. So here are a few results. So the first result we have here is on the civil airlines model. And so this is simply a test on our flow solver that we've done. And so we've compared our scalability against the star CCM plus industrial solver. And so we can see that the scalability is pretty good. And for a lab developed solver, this is a really good result in terms of scalability, especially in comparison to the industrial solver. But obviously, there are still some things to improve, especially in the inter-node communication. And so this is something that we've tried to address with the Chapel team. And especially there's something that we've implemented quite recently, which is the usage of periodic exchange buffers. So this idea was brought to us by Engin, actually, and it proved quite useful, as we can see here. So the test case is a flow solver case where we have 100,000 cells per core. And so we can see that initially, without any optimization, the computation takes around between 1,000 and 1,200 seconds. And when integrating that prediction buffer solution, we are basically slashing by half the compute time. So this shows that optimizing internet communication is quite crucial for the speed up our solver, as just one implementation of prediction buffers have slashed the compute time by half. And so, yeah, in conclusion, a quick word on how we feel as students about Chapel and its usage in the CHAMPS language. And so Chapel is quite low barrier to entry. And so this is crucial for student-driven lab because most of the students come from an engineering background. And so we've got initially little to no experience in HPC or coding. And so Chapel makes it quite easy to learn for the students, actually. And so the language also makes it easily transferable to industry via staff rotations or short-term internships. And also, the Chapel language allows seamless parallelization. So especially, I'm talking about the coformal statement and basically the whole of the Chapel paradigm. It makes it very easy to parallelize, which is crucial in CFD development. But obviously, there are some areas to be improved on, such as the compilation time, which can be reduced, as it basically slows the productivity by a lot because we need to compile every time we need to debug. And also the scalability, especially for very, very big problems that use hundreds of millions or even billions of cells. The scalability in that part can be improved on our side. And so finally, we would like to thank Engin, Jade, and Brad, as well as the whole of the Chapel team for their continuous support, insightful discussions, and encouragement throughout this work. So thank you very much for listening. And if you have any questions, feel free to ask.
Thank you so much, Anthony. Any questions, please? I've got a question from Luca. Luca, go ahead.
I have a question about like interface usability. Maybe you hadn't just missed it, but how do people use CHAMPS generally? Does it have like programmatic interface that people can program in, or can you like do like meshing and in some GUI and then plug the CHAMPS as a solver, like integrating ANSYS, for example, or similar? So what is the user workflow?
Yeah, so good question. So basically, we use the CHAMPS software as a standalone, which means that we create the meshes by ourselves using external software. And then we input that mesh into the CHAMPS software, and then we solve it by setting input files, and we get the results printed. But the only external software that we're using are basically external libraries, such as the Intel MKL or Metis, or basically libraries that allows us to do parallelization and partitioning. But every computation is done inside Chapel otherwise.
Okay, but like if I want to develop like a model, how do I start? Like
Yeah, so to implement a model, basically you contribute directly by the code. So
okay, yeah, sure. Thank you.